Hello, and welcome to the presentation on failure theory overview with a focus on composites. My name is Farouk Zahid, and I'm doing this presentation for an aerospace structures class at Virginia Tech. Let's get started. So shown on the left is the stress-strain graph of a low-carbon steel, while on the right is a comparison of a few materials and composites. Keep in mind that yield strength is most important for ductile materials, as that is where they begin to deform plastically, while ultimate stress is most important for brittle materials, as they do not deform as much, but will catastrophically fail when reaching ultimate strength. Most of what we've done so far deals with ductile materials. So let's lay down the groundwork for the discussion. I won't go into derivation of these theories, but I want to mention a few important things. Stress is described on an element easily by looking at the three principal stresses, which are ordered as shown here and are orthogonal to each other. To predict the stress state and failure states of a material, we want to compare these principal stresses to the yield or ultimate states of the material. Recall that the components of a stress state are the stresses causing a change in volume and the stresses causing a change in state. These are also referred to as the hydrostatic and the distortional or deviatoric stresses. Yielding is only caused by the stresses which cause shape distortion. Here, these components are expressed in terms of the principal stresses and put into matrix form, but these can also be written in terms of any stress state. Tresca failure theory, or maximum shear stress theory, says that yielding occurs when the maximum shear stress is equal to shear stress at yielding in a uniaxial tensile test. It's a function of principal stresses instead of shear stresses. It looks like the difference between sigma 1 and 3. If you want to think about this more, try your hand at drawing out Moore's circle for a tensile tested yield, where sigma 1 is at sigma yield and both sigma 2 and 3 equal 0. Moving on, let's look at the von Mises theory, or maximum distortion energy theory. Instead of comparing your maximum shear stresses, now we'll look and compare distortion energy at yield. Remember that distortion energy is the portion of strain energy corresponding to the deviatoric stresses. Distortion energy per unit volume can be calculated in terms of principal stresses, which can then be related to the strain density at yield to give the equation under von Mises in yellow. So we're going to dive into some different kinds of failure theory, but first we need to know what exists at a high level. First is limit or non-interactive failure theories, which only take into account the effect of one stress or strain component for each failure condition, ignoring interaction between the different stress components. An example of this is maximum stress or maximum strain theories. We won't be discussing these. Second is fully interactive theories, which, as you might guess, use equations with all stress components included. The stresses in different directions are not decoupled and do affect failure simultaneously. We'll discuss one soon, but what's important is the difference between fully interactive theory and our final category of failure mode-based theories. Interactive theories are very useful, but they do not predict the way in which the material will fail, which the third group of theories can. This can be important as some types of failure can be more critical, especially in the case of a composite. The Tsai-Hill failure criterion is a fully interactive theory which attempts to take account of interaction in a multi-axial stress state. In our case here, we only look at uniaxial stress to determine our principal stresses. It is widely used for anisotropic composite materials, which have different strengths in tension and compression, and predicts failure when the failure index in a laminate reaches 1. You can see the formula here in terms of principal stresses, with the stresses in the denominators being the allowable strength in the longitudinal direction, transverse direction, and the in-plane shear between the two directions, corresponding to sigma 1, 2, and 3 max in a composite. Note that these can be different depending on compression or tension, and that after solving, the mode of failure is not given, only a Boolean true or false. The example case shown with equations for the principal stress can show how the apparent strength of a material or composite depends on the orientation of the material in relation to the applied stress. The Tsai-Hill criterion has been further developed and generalized into the Tsai-Wu criterion, which includes stress and strength interactions in the fiber and matrix directions. It relies on experimental constants and is more complex than this, but it's interesting. I recommend reading into it. Science Direct and Wikipedia both have useful pages for references that you can peruse at your leisure. Let's move on. Now we're moving on to Hashin-Rotem failure criteria. This is the final category of failure mode-based or partly interactive theory and was initially developed for unidirectional polymeric composites, the initial paper being published in 1980. Having been developed for a particular case, it may lead to large approximations when dealing with laminates or non-polymeric composites. The important thing to us right now is that by looking at this, you can see that this theory shows you failure in numerous cases. Fiber, matrix, and interlaminar tensile and compression states. We can evaluate relatively simple equations with data to determine failure modes given principal stresses. Of course, developing these theories wasn't so simple, and the contents do require experimental data. The T and C subscripts denote tension and compression allowable strengths. XT, YT, and ZT denote allowable tensile strengths in the three respective material directions. And S12, 13, and 23 denote allowable shear strengths in the respective principal material directions. For further reading, reference Hashin's paper, Failure Criteria for Unidirectional Fiber Composites. It is on my references slide at the end. The Puck failure criteria is another failure mode theory. The Puck failure criteria is another failure mode theory which gives us information on modes of composite failure, just like the Hashin criteria. Both employ stress strength-based failure criteria, but they differ in matrix cracking predictions. Hashin only distinguishes between transverse tension and compression, while Puck adds a third mode named mode C to cover the possibility of an inclined fracture plane. The inclination is determined by the ratio between the transverse normal and in-plane shear stress. These three modes are depicted in the images on the right. Also shown on the left are the formula for fiber tension and compression failure indices for mode A, but the indices exist for the same six on the previous slide, as well as more indices for mode C. We won't go into the math here as it is a little bit much to fit on a single slide, but being aware of these differences and of different kinds of failure theory is vital for materials analysis. Make sure you know what you're trying to analyze when you do so. I hope that you enjoyed and learned a little bit. Thank you and take care. This is my reference slide, and I recommend that if you have any interest that you take a look through some of these. All of them have a pretty good amount of information, and just good reads if you like this kind of stuff. Thank you.